Before moving ahead toward characteristic functions, Fourier transforms of measures, I'd like to take the opportunity to highlight one more very useful result about weak convergence. We've seen that weak convergence is the weakest of all notions of convergence of measures that we've encountered so far. It's certainly weaker than total variation convergence, and it's weaker than all of the notions of convergence that come from random variables: almost sure convergence, LP convergence for any p, and convergence in probability. However, there is a connection between weak convergence and the strongest of those, almost sure convergence, which often comes in handy, and that is Skorohod's theorem. Skorohod's theorem says the following: if μn and μ are Borel probability measures on a separable metric space S, and μn converges weakly to μ, then we can couple all of the μn's and the μ. We can realize them all as the distributions of some random variables on some auxiliary probability space in such a way that the random variable yn has distribution μn, the random variable y has distribution μ, and yn converges almost surely to y. Now, this does not say that any coupling of these yields almost sure convergence. That is almost surely false. It says that we can couple them in a way to get almost sure convergence, but it doesn't tell us that in doing so we can say anything meaningful about the correlations between them. The proof of this theorem, as stated here generally, is very involved. The probability space that one constructs them on in this level of generality is the unit interval crossed with the infinite product of the metric space S with its Borel sigma field, and the probability measure used is a well-chosen infinite product measure that introduced lots of complicated correlations between the YNs. It would take us several lectures to go through all of the details, and again we're going to skip all that and satisfy ourselves with proving this theorem in the special case that the metric space is the real line. So we will prove this theorem for real valued random variables. In that context, we can again use the order properties of the real line and prove this theorem using the tools of cumulative distribution functions. And it turns out that the key idea will be inverting cumulative distribution functions. Suppose that f is the CDF of some real valued random variable. That is, f is equal to f mu for some Borel probability measure mu on the real line. If f is actually strictly increasing, which is the same as asserting that that Borel probability measure never assigns zero probability to any non-empty interval, then the function f is of course an invertible function. A strictly increasing function can be inverted, and its inverse function maps the open unit interval into the real line. Open here because since it is strictly increasing, f never achieves the values 0 and 1, they are only achieved in the limit. Now, since f is an increasing function, its inverse is also a non-decreasing function, which therefore makes it measurable. And so we could think of this function as a random variable on this measure space. If we equip that measure space with its Borel sigma field and with the Lebesgue measure, in other words, the uniform distribution on that interval, then we can compute what the distribution of this random variable f inverse is. In order that we don't get confused with notation, let's call this random variable y, and we'd like to calculate its distribution. We'll do that, of course, by computing its CDF. The CDF of y is the probability that y is less than or equal to t. The probability measure we're using is the Lebesgue measure, so that's the Lebesgue measure of the preimage of the interval from -infinity up to t under y. But since y is an inverse function, it is invertible, and so the preimage is the same as the image of the inverse. And since f is a non-decreasing function, it maps the interval from -infinity up to t to the interval from the lower limit 0 up to f of t. But the Lebesgue measure of that is just f of t minus 0. So what we've seen is that the CDF of y is f. f, which was the CDF of the starting measure mu. So that means that this random variable y has mu as its distribution. So that's a neat way to construct a random variable that has a given measure mu as its distribution. It apparently only works in the case where the cumulative distribution function is invertible, that is, that it's strictly increasing. But it turns out that we can modify this slightly to work in total generality. Graphically, how do we invert a function? We rotate it around the line y equals x. How could a general CDF fail to allow that operation? If the CDF has horizontal flat bits, then when we rotate that around, we'll get vertical parts, which is a problem for a function. But it's not a problem when the function is non-decreasing. We just have to appropriately interpret those vertical parts as jumps. And if we want the new function to be a cumulative distribution function, that tells us how to interpret it. Making the function right continuous means putting the value at the top of the jump. We can formalize that as follows. Given any CDF f, we define f back as f back of x is the largest y for which f at y is less than x. We also define f forward by f forward at x is the smallest y for which f of y is bigger than x. You can quickly work out that if f were, say, continuous and strictly increasing, that both of these are just equal to the inverse function. More generally, a CDF may not be strictly increasing and may not be continuous. That is, it can have jumps and it can have flat bits. And in that case, we can see what the values of f back and f front are. If a is the height of a flat part for f, then the left limit of that flat part is f back, and the right limit is f forward. On the other hand, it's easy to check that if we have a vertical jump, or if we have a continuity point, f back and f forward are actually equal. So f back and f forward are two interpretations of the inverse of f, one of them assigning the mass to the top and the other to the bottom of a new vertical jump. And let's figure out which one is which. First, from these observations, we can see that f back is always less than or equal to f forward, and they differ only at points that are heights of flat spots. For example, here. Now let's look at that set of heights of flat spots. That is a countable set. Why? Because for each such x, the open interval from f back of x up to f forward of x is non-empty, and therefore must contain some rational number. Now, since the function is non-decreasing and strictly increasing off of the preimage of e, these intervals for different x's are disjoint. And that means that there are distinct rational numbers corresponding to all of these intervals. So if there were uncountably many of these x's, there would have to be uncountably many rational numbers. And since there aren't, we see that E is a countable set. Now here is a key property, which I've alluded to in the pictures, which basically tells us that f back is a version of the inverse of f. For any x in the unit interval, f of f back of x is greater than or equal to x, but if we approach f back of x from below, then that limit is less than or equal to x. And so, for example, if f happened to be continuous at this point, it would follow that f of f back of x is equal to x, and so we do get the inverse. Now, why is this property 3 true? If y is bigger than f back of x, then f at y is bigger than or equal to x, just from the definition. F back of x is the largest y for which f at y is less than x, and so if f at y is bigger than x, then y must be bigger than that supremum. So using that and the right continuity of f, if we just take y down to f back of x, that gives us that f of f back of x is greater than or equal to x. Now conversely, if y is less than f back of x, then f at y is less than x. Indeed, if y is less than or equal to this supremum, then that means that there must be some y prime bigger than y so that fy prime is less than x, but because f is non-decreasing, it then follows that f of y is less than x as well. Now, if we had continuity, we could conclude that f of f back of x is less than or equal to x by taking the limit. We don't necessarily have continuity, but what we get instead is exactly this. If we take the limit as y goes up to f back of x, we get that the limit is less than or equal to x, which is this statement here. So f back is close to an inverse of f, and so is f forward because of property 2. It equals f back except on a countable set. Now this f back function, which is defined for every CDF f, does the same job that we saw on the last slide and allows us to easily construct on the unit interval a random variable with given CDF f as follows. If we fix our favorite CDF f and we define y to be the random variable on the unit interval, which is just the function f back, then with respect to the Lebesgue measure on the unit interval, that random variable has that f as its CDF. In other words, if that's the CDF of a measure mu, then the distribution of this random variable y is the measure mu. Let's prove that. Of course, first we have to prove that this is a measurable function, but that will come out of the proof right away. For any real number t, let's suppose that y of x is less than or equal to t for some x. Well then, by that inequality 3 that we had on the last slide, we see that x is less than or equal to f at y at x, which is therefore less than or equal to t. But actually that characterizes this set where y of x is less than or equal to t. The set of all x's in the unit interval where y of x is less than or equal to t is equal to the set of points in the unit interval intersected with the interval from 0 up to f at t. So this proved the forward containment there, and we need to prove the reverse containment there. That is, we need to see that if x is less than or equal to f at t, then y of x should be less than or equal to t. Well, y of x is the supremum over all y's for which f of y is less than x. But since f at t is greater than or equal to x, that means that t is above this set and therefore above the supremum of this set as well, which shows the reverse containment. So that proves this fact, and we see from this fact that y is a measurable function because this shows that the preimage of y on the interval from minus infinity up to t is of this form here, an intersection of two intervals, which is of course a Borel set. And since the family of intervals from minus infinity up to t generates the Borel sigma field, it follows that y is indeed a Borel measurable function. Now from here we can just calculate that the Lebesgue measure of the set where y is less than or equal to t is the same thing as the Lebesgue measure restricted to the unit interval of the interval from 0 up to f at t, which is exactly equal to f at t minus 0, or f mu of t, as desired. Now, by the way, this gives us an actual constructive way to produce random variables of a given distribution. Another way of phrasing what we just wrote is that if mu is any Borel probability measure with CDF f, and if u is a uniform random variable, then f back of u is in distribution equal to the given measure mu. That's how computer algebra systems generate samples from normal random variables, or exponential or Poisson random variables. They have an algorithm for producing random samples or pseudo-random samples of a uniform distribution, and in order to get pseudo-random samples of any given distribution, they just do this and are programmed in with f back for given distributions of interest. We're going to use this construction in a theoretical way to prove the baby Skorohod theorem. Baby in this case meaning in the case for real valued random variables. So again, the theorem is, now that we can state it precisely, if mu n is a sequence of Borel probability measures that converges weakly to a Borel probability measure mu, then if we define yn to be f mu n back and y to be f mu back, which are random variables on the unit interval equipped with Lebesgue measure, then yn has mu_n as its distribution, y has mu as its distribution, and yn converges almost surely to y. Now, in the lemma we just proved, this was the result. So all we need to do is show that yn converges almost surely to y. And in fact, we're going to characterize the set where convergence fails. It's exactly that set E, the set of heights of flat points in the limit distribution, f mu, the set of points where f back is strictly less than f forward. That set is countable, as we showed, and therefore its Lebesgue measure is 0, which shows, once we've seen that this is true everywhere else, that yn converges to y almost surely. So let's prove this. We know that mu_n converges weakly to mu, which means that f mu_n of y converges to f mu of y for all points y at which f mu is continuous. So fix one of those points of continuity y of f mu. That means that f mu_n of y converges to f of y. Now, let x be a point where y of x is bigger than that continuity point y. Remember that y of x is the supremum over all points y prime at which f mu of y prime is less than x. So since y is less than that supremum, and again using the fact that f mu is a non-decreasing function, it follows that f mu of y is less than x. But therefore from this limit we can conclude that f mu_n of y is less than x for all sufficiently large n. But that means that yn of x, which is the supremum of all y's for which f mu_n of y is less than x, must therefore be greater than or equal to y for all sufficiently large n. Now that holds true for all y less than y of x that are continuity points of f mu, and of course continuity points of f mu are dense because f mu is a non-decreasing function and therefore has only countably many points of discontinuity. And so taking lim_inf, we find that the lim_inf of yn of x is greater than or equal to y of x. Now if x is not in E, then f back of x is equal to f forward of x. Now we can repeat the exact same argument, starting with a y chosen in the continuity set of f mu that is bigger than y of x, identifying y of x of f forward. But f forward is the infimum of these where this is greater than x. And you can run through exactly the same argument line by line, and what you'll get, since all the inequalities are reversed, is that the lim sup of yn of x is less than or equal to y of x. And of course, putting those two together gives us the limit statement that we desired, concluding the proof. Before we sign off on Skorohod for now, let's see how this theorem can be used to give a proof of a nice extension of the continuous mapping properties of weak convergence. This is sometimes called the continuous mapping theorem. Suppose that f is a Borel measurable function of the real line, and suppose that xn converges weakly to x. Now, it follows quite easily from the definition of weak convergence that if f was actually a continuous function, then f of xn will converge weakly to f of x, because the definition of weak convergence involves testing against continuous bounded functions, and a composition of a continuous bounded function and a continuous function is a continuous bounded function. But we can use Skorohod's theorem to prove that this holds true even if f is not continuous. It only has to be continuous almost everywhere that x can see it. In other words, if f is a Borel measurable function such that the weak limit random variable x has probability 0 of being in the discontinuity set of f, then we get f at xn converging weakly to f at x. And if in addition that function f is bounded, then we get convergence of the expectations as well. I should mention that a version of this theorem corresponding to metric space S valued random variables holds true, and the proof is no different if you accept Skorohod's theorem holding in that context as well. Here's the proof. We're just going to take our random variables xn and x and replace them with random variables yn and y on some probability space where yn converges to y almost surely. That's what Skorohod's theorem tells us we can do. Now, having done so, fix any continuous bounded function g. We're going to test integrals against f at yn, which has the same distribution as f at xn, against g. And when we do so, we're going to have to look at the discontinuity set of g composed with f. Well, the discontinuity set of g composed with f is contained in the discontinuity set of f. Because if f is continuous at a point, since g is continuous everywhere, g composed with f is continuous at that point. It follows that the probability that y is in this discontinuity set of the composition is less than or equal to the probability that y is in the discontinuity set of f. But this is a probability that depends only on the law of y, and y was chosen to have the same distribution as x, so that's the probability that x is in the discontinuity set of f, and that is assumed to be 0. So we get that y also has probability 0 of being in the discontinuity set of g composed with f. Now, as such, we can just conclude immediately that g composed with f at yn converges to g composed with f at y almost surely. And that's because if g composed with f is continuous at some point, then we get this by the definition of continuity, and yn converges to y on a set of full measure, and y is almost surely contained in the continuity set of this function here. Now, moreover, both sides of this limit are less than or equal to the supremum of the bounded function g, and therefore we can apply the dominated convergence theorem to conclude that the expected value of the left side converges to the expected value of the right side. But of course, by the change of variables theorem, this is just the integral of g against the law of f of yn, and this is equal to the integral of g against the law of f of y. And by our choices of yn and y, we can replace them with xn and x here, concluding the proof of the first part of the statement, in order to also conclude that we get convergence of expectations. We can just take g to be a function that looks like this, where this is minus m, this is m, and this is the function f at x equals x, where m is chosen to be the supremum of the function f. In that case, since f at xn and f at x never see heights above here, as far as they're concerned, this is just the identity function, and this will just become the expected value of f at xn, and this will just become the expected value of f at x. And that concludes the second part of the statement of the theorem. We will see other uses for Skorohod's theorem in the coming days, and we will see many uses for Prokhorov's compactness theorem as we go. We now turn to a major analytical tool that we can use to robustly analyze weak convergence, that is, characteristic functions, Fourier transforms of measures.